Okay, so here's a look at week 15 Math Excel homework number 3 and number 10. Now, my equation might be different than the one that you see on Math Excel, but it is pretty indicative of what you'll encounter, so the process should be very much the same. In number 3, we're given the horizontal distance that a projectile will travel in the air by this particular equation. Now, the letters might be a bit misleading. I'm not entirely certain if they are or not. R in this case actually stands for the horizontal distance that the object will travel. So the distance that the projectile will travel, this v sub 0, this combination of v and the subscript is our initial velocity, how fast we throw the object or start the object on its motion. The theta value is the angle relative to the ground, and g is our gravitational constant. It's the gravity is shown here in the problem. So with all of those components, all of those variables identified, as we read through part A, then we can decide where each of the numerical values should go. So we can throw a baseball with an initial speed of 33.2 meters per second. That's going to be our V naught, V sub 0. The question becomes, at what angle should you direct the throw? So this is what we're looking for. We're looking for the theta value so that the ball will travel a distance of 107 meters. Well, our 107 meters is the R value in this case. Keep in mind, too, that G was described as 9.8 meters per second squared. So we've got V, we've got G, we've got R, we've got V, G, and R. The only thing that's missing is theta, so we should be able to solve for theta with a bit of algebra. So off to the side, I'm going to write 107. That's the distance traveled. 107 equals, I have to reference this again. Our initial velocity was 33.2 squared times sine of 2 theta. Divide that by g 9.8. So ultimately our goal is to get this theta value by itself for part A, and there are several ways that we could do this. You might see this as a double angle identity, and you may be tempted to rewrite this as a using a trig identity. And you could, sine of 2 theta is the same as 2 times sine theta times cosine theta. The problem that I have with that is that if we were to make this substitution, now we're going to have two different trig functions evaluating at the theta angle measure that we're after. And that could be tricky to solve. So I personally would avoid that. Instead, what I would do is remove all of these ancillary components in trying to get this theta value by itself, and then use traditional trig equation approach to isolate the theta. So I'll show you what I mean. First, I would multiply both sides by 9.8. And you could go to the calculator and find out what that is. I'm just going to avoid that for right now and use the calculator in one big shot at the end here. After I multiplied both sides by 8, I'll divide both sides by 33.2 squared. And then finally, I need to eliminate this sine function from the right side of the equation, and I'll do that with a sine inverse. If I apply the sine inverse, I know the two sine values will eliminate, and I'll just need to apply a sine inverse around whatever the result of this calculation ends up being. And then, of course, to isolate theta, we can divide the entire equation by 2. And so this is quite a large expression, but it's exactly what we would have to do in order to solve for theta. And as I said before, you could have evaluated this whole group of numbers and gotten a single number. You could have punched that number into sine inverse and then divided that number by 2. The only concern that I have is along the way you might round differently at each step, or during the process of rounding, you just might lose some accuracy. So these are the answers that I'm going to obtain, and I'm going to get them by using my TI Nspire calculator, although any calculator with trig functions and inverses will do. So part of the reason why I like the Nspire is that I can make the expression in this calculator look just like the expression that we had written on paper. And as long as I'm happy with what I had written on paper, then I should be okay with what we obtain as a result in the calculator. And so a real quick check here, I think we're in good shape. If you had to use a different calculator other than this one to obtain the result, again, complete it piece by piece, we should end up with the same result. Now I got 0.6287 and my calculator's in radians. I didn't double check, or I didn't check what the solution is expected to be. Okay, so the solution is supposed to be degrees, so we better change that. On this calculator, it's in the menu in the top right-hand corner. If you highlight your previous expression and then tap enter, it copies it down. So recalculating the same expression, this time with our calculator in degrees, should give us a result in degrees. And now we've got 36.0259. 36.0259 when rounded to the fourth decimal point. And so this solution suggests that if we're throwing a ball and we start its path at 36 degrees, then this ball will travel a total distance of 107 meters. Now there is a bit of a problem, since this problem originated with a 2 theta. There's typically 2 solutions by the time we're all done. So here's one of them. Here's our first theta value, but there's another one. There are a couple ways to obtain the second answer, but what I'm going to do is I'm going to come back to this expression here, and before we divide by 2, we had something that looked like this. 2 theta was equal to sine inverse of this expression. And if we were to evaluate that before we divided by 2, let's just see what that result looks like. And so if we evaluated this expression, sine inverse of 107 times 9.8 divided by 33.2 squared, we get the angle 72 degrees. Now this 72-degree angle is not the angle at which we would throw this ball, but it's twice that of the angle, because this result is 72.05 is equal to 2 theta. And so of course when we divide this by 2, we get the 36 degree angle that we were after over here. But I need to call your attention to this solution for just a second. This solution here, this 72-degree angle, let's say about this position in a unit circle, that's not the only position that has this particular y value. Now, I'm not really that interested in what the y value is here, but that's what the sine function is essentially establishing. What's the y coordinate where this 72-degree angle strikes the unit circle? What I am interested in is the other angle that contains the same y coordinate. In this case, it happens somewhere over here. And so while this angle measure was 72 degrees, this angle measure here is 72 degrees less than 180. So if this is 72 degrees, then this is 72 degrees as well. And what I'm interested in is actually this guy right here. I want to know what that angle is. So if we use our calculator and simply take 180 minus the answer that we got just a second ago, we see 107.94. We'll call that 107.95 with rounding. So while 2 theta is equal to 72 degrees or 107 degrees, then when we divide by 2, we should end up with two angle measures that'll actually produce the same result. This, of course, is the 36.025 or 36.03 when rounded. And this result here, when divided by 2, produces the angle measure of 53.97. 53.97 degrees. And so that's easy to overlook, but apparently not only can we throw this ball at a 36-degree angle against the horizontal, but if we tossed it a little bit higher upward at a 56-degree angle, or I'm sorry, a 53-degree angle, it too would move or fly the 107 meters. So to answer your part A, make sure that you include both of those. Make sure that you include both angles because the problem is looking for a solution set. And again, the way we obtained those two angles was not just relying on the calculator's result for theta, but overriding that calculator for just a moment and thinking about our unit circle in that process. Now for part B, I would probably move to a graphing calculator here. Desmos is a good choice when you're working at home, or if you've got a graphing calculator that you're comfortable with, you can of course use that. But Desmos is so fast, and if you put it on your on a cell phone or a tablet or something like that with a touch screen, it's very easy to manipulate on screen. But in order to find the maximum distance that you can throw the ball, well, all we really need to do is graph this function in terms of r based on the optimal angle. And if you recall from physics, in order to optimize the distance that you can throw a projectile, you want this theta value to be 45 degrees. That way you're not losing any of your energy by throwing it up too far vertically, or you're not losing any of your energy by throwing it at a too shallow of an angle. The optimal angle is 45 degrees, right in the middle between vertical and horizontal. So if we jump out to Desmos, I would just write that function, but instead of using r's and thetas and g's and v's and all those letters, I'm just going to use x's and y's. So y is going to represent my horizontal distance now instead of r. And by pressing the division sign or the slash key, that should give us a fraction bar. Across the top, we have the same velocity as part A, 33.2 meters per second squared, times sine of 2 times theta. Now, theta is 45 degrees here. We know that 2 times 45 is 90. Just keep in mind that we're not throwing the ball at 90 degrees, but we're throwing it at 45. Just happens to be the process of the equation that multiplies that 45 by 2. Our g value is 9.8. And I just had to double check something here. The calculator was in radians mode a second ago, so I switched that over to degrees, and we can now see that the maximum distance is going to be 112.47 meters. Now, you may be wondering why I used, let's see here, oops, we're supposed to round to 1 decimal point. Why did I end up using a graphing calculator here? Well, let's just change something. If I go back to Desmos, and let me switch this to projector mode to make this stand out a little bit more. What if I let the angle be a variable here? So if I threw the ball at a 0-degree angle, that's what this first number represents, then the ball is going to go a distance of 0 feet. If I throw it perfectly horizontal, it's not going to go anywhere. And if I were to drag my cursor, say, to here and throw my ball at 1 degree, if I can get this to stop, then the ball is going to travel about 3.9 feet. As I increase the angle, which is my x-axis here. As I increase the angle, then the ball should travel farther. This graph does not show the trajectory of the ball. It just shows what distances the ball might travel based on the trajectory that I do throw. Now, a second ago, we were throwing the ball at 36 degrees, and that ended up netting a 107-meter distance. Well, let's see if we can try to verify that. At 36 degrees, it's not going to be perfect, but about 36 degrees, yep, sure enough, the ball was traveling about 107 meters. But also at 50 some odd degrees, 53 degrees, I think it was, again, we were traveling about 50 or 107 meters. So this graph seems to support that. And as it turns out, if we go right here in the middle, the peak of that curve occurs at this point, 45, 112. And again, this is saying that if we were to throw the ball at 45 degrees, it would travel a distance of 112 feet, and that ends up being the maximum. Now, having that graph in mind helps us to see the answer to part C. Which of these three options matches the graph that we just showed? Well, what you got to pay attention to here is your scaling. We've got 30, 130, 0, and 90 written in the corners of each of these graphs. Those represent the axis scale. So along the y-axis, we're going to go up to 130, and on the x-axis, we're going to go out to 90. So with my calculator, I would try to match that the best I can. It doesn't have to be perfect, but if we can get the window pretty close, then that should give us a better representation of the graph with which we're looking. So let's see, this x-axis should go out to about 90, and the y-axis is going up to about 30. So I'm looking for a graph that has a relatively high peak to it. So I don't like option B I don't like option C in this case because that peak seems a little bit low. Option A in this window, well, it's not a graph that's tailing down. So A is no good, C is too low. I would choose B as my option here. For number 10, well, this one's an equation that we need to solve for C. Doesn't really have an application component with it. But it's a nice problem to look at, and I chose it because of the double angle identity here. So if our job is to solve for C, find out the value of C, we just got to get C by itself. And one thing we can do is subtract this entire term to the right-hand side, and then we'll be left with C equals 1/6 cosine 2x minus 1/3 cosine squared x. And that's okay. The trouble that we have is that the arguments inside of each trig function don't match. So it's not like this is a quadratic equation that can be solved because the arguments on the interior here just don't agree. So we've got to do something a little bit different. So what I think I might try here, and again, this is the problem with this trig unit, is that sometimes you just have to try things to see what sort of result you'll end up with. But I'm going to try to rewrite cosine 2 theta using one of the double angle identities that was discussed on day 56. If we go out to day 56, we had the handout that had these double angle identities, and there happen to be 3 of them for cosine. Cosine of 2 theta, or 2x, depending on what variable you use, can be written in one of these 3 ways. Now, any of them are equivalent to cosine 2 theta, but the one that I think I want to try here is this guy down at the bottom, because I've already got an equation that contains a cosine squared, so I'm going to go ahead and rewrite cosine 2 theta in terms of cosine squared. So what I have is C equals 1/6, and this guy in the box here turns into 2 cosine squared of x minus 1. So all of that in this parenthesis grouping symbol has replaced the box, and then we tack on the stuff that we haven't messed with yet. Cosine squared x And now we can distribute. So C is equal to a sixth of 2. Well, that's 1/3 cosine squared x minus 1/6 minus 1/3 cosine squared x. And that's pretty interesting because I have one group over here, 1/3 cosine squared x minus 1/3 cosine squared x. So these two are going to cancel each other out. And ultimately, we're left with C equal to negative 1/6. So really, this equation is an example of trickery. It's a fortunate equation in that the double angle identity was the key to help us solve this pretty directly. So I would suggest that you try that on your example too. I hope this helps.